In the last video, I completed the VGA driver for the Hack computer. And so in this video, I want to take the VGA driver, combine it with some video memory, and produce the screen component that is defined on page 90 of the Elements of Computing Systems. So let's define some inputs and some outputs. First thing is, of course, we'll need the clock. Now the next thing defined is a load flag, because this component from the perspective of the CPU just looks like memory. So, it needs to be able to load memory. The CPU does. It needs to be able to load memory. It needs to be able to read a value out of memory, and with the load, it needs to be able to write a value into memory. So this I/O interface looks basically just like a RAM component, with some additions we'll talk about in a second. So it needs a load signal, and it needs an address input for addressing memory. Now, unlike the book, I'm defining this as 16 bits. True, the actual memory that's being addressed is only 13 bits, but there's a reason why I'm going to take all 16 bits in as input, and we'll see that in a bit. Obviously, if we're going to write memory, it needs the memory value to be written. And on the output side, if we're reading memory, we need to know what the value read is. Now, according to the book, that's the complete I/O interface. However, this is actually driving a physical screen, as opposed to, in the book when they designed this was a simulation. So we're going to need the physical pins that are required to actually drive a VGA monitor. And so let's go ahead and add the VGA driver so we can hook those up. Let's put a tunnel on our output address. So let's talk about how this component needs to work. So if you watched the last video where I built the VGA driver, you'll remember that the driver is constantly asking for the next address of video RAM, and then reading the value in, and then rendering the value to the monitor. And it's, the driver itself is not under CPU control. It just free runs, constantly asking for addresses and taking the memory and pumping the bits to the display. However, the CPU also needs to be able to access video memory, because it may be necessary to read the 16-bit value out and twiddle a few bits and then write the value back in. So you may see the dilemma: what happens if the CPU and the VGA driver simultaneously need to either read an instruction from or write an instruction, or, in the CPU's case, write an instruction to RAM? How do we arbitrate that access? The way it's normally done, modern days, is that you have dual-ported RAM, which means that you have two different addressing schemes where you can address the RAM and get a value back from two different buses, essentially. And most FPGAs support block RAM that have that capability. However, I believe it's the case in Logisim today, at least, there is not a RAM component that supports that. While it would be possible to build one of those, and I may well do that, there's alternatives and workarounds for that. And so I'm going to implement that workaround and basically build some arbitration logic to allow single-ported RAM to be able to work. If both sources simultaneously need access to RAM, who's going to win? And so my proposal is that I would rather not block the CPU. And if the VGA driver needs to access, read a piece of memory, and RAM is busily servicing another request from the CPU, I would rather the VGA driver just get zeros for that particular word. My hunch is that the CPU will hog video RAM much less than the VGA driver ultimately would, because of course the VGA driver is trying to read RAM every 16 bits. And so an occasional dropout here and there, especially with our VGA rendering 70 frames a second, my guess is not going to be noticeable. Now, we're not trying to build a production system here, so it may be too annoying to be workable, but at this point, I think we're just going to go with it. So let's add in some video RAM. And this video RAM is 13 bits address-wise and 16 data bits, giving us 8K. And let's make this smaller. So we've got our two address sources to consider, right? So NA is the address from the CPU being asked for or being referenced for writing memory. And then you have this address coming out of the VGA driver where it's always asking for a data value to render. And so in order to build our selection logic, we need to know when it is the CPU is actually asking for a piece of memory from video RAM. Now, this video RAM is only 8K, and of course our address for memory can go all the way up to 32K. So we need some discrimination logic to tell us when we're actually being asked for a piece of video RAM. So let's just build a component that can do that for us. So we'll call this VRAM access control. So let's define our ins and our outs. So VRAM access control, very simply, will take a 16-bit input, which is the address being asked for, and it'll just take a pin on the output that'll just be a 1-bit that will tell whether or not this is VRAM that's being accessed or not. And so we need, let's just use a splitter. So when is it the case that video RAM is being accessed? Where is that in the address map? If you go to page 92 of the Elements of Computing Systems, it actually tells you the address range of video RAM. It says access to any address in the range 16,384 to 24,575, hex 4000 to hex 5FFF, results in accessing the screen memory map. So let's put an AND gate out here. And before we hook that up, let's just use our calculator and see if we can look at a pattern here. So the bottom of the range is 16,384. And we can see that the binary value is 010 and a whole bunch of zeros. Let's clear that and let's put the end of the range in. 24,575. And again, we see 010 and then all ones. So that should give you a pretty good indication of what it is that we need to look for that encapsulates the entire range of the 8K of video memory address. So if we had an AND gate with 3 inputs, with the top being negated and the bottom being negated, and we hooked it up like so, then we know that if we have an address following this logic, we have an access request for video RAM. So let's go back to our screen component. So we'll take our input address being asked for. And so we need to determine whether or not we want the VGA driver's address request or the CPU's address request to be put through to video RAM. And so we can do that with a multiplexer very easily, a 1-bit selected multiplexer. And it's only going to pass 13 bits because our RAM is only 13 bits wide address-wise. And very simply, our video RAM bit coming out of the access control will feed the mux. So we know that when this is 1, this will be the value that will need to be coming from the address request from the CPU, because it's the CPU that is the one asking for a piece of memory from video RAM. Now, the only problem is that this is a 16-bit address, but we're only going to pass the lower 13 bits to the video RAM, so we need a splitter to convert this to 13 bits. And you may ask, well, why don't you use a bit selector to do this, Chuck? And I would encourage you to try that yourself and synthesize the design. And back in the comments, you can tell me why that doesn't work. I actually know why it doesn't work. There's a bug in Logisim that I'm going to file and probably fix, but I encourage you to try it yourself. And this is when you try to synthesize VHDL. It may work fine with Verilog, I'm not sure. And so when VRAM is 0, then the CPU is not asking for video RAM. And so in that case, the VGA driver gets control. So whatever it's asking for, it gets. And so the output of this mux now gets connected to the address line of the video RAM. So let's talk about write enable, writing data into video RAM. It's relatively easy. So when we have when the CPU is trying to address video RAM and the CPU is trying to load it, well then obviously that's when write enable needs to occur. Let's use an AND gate to do that. Now let's go ahead and put the clock in there. And then finally, any data value that we want to write into memory, again, doesn't need to be arbitrated because it's only coming from the CPU. So in that case, that is just simply a direct wire from input. So for the output of RAM, obviously this needs to go to the output of the component. So we need output of RAM to be wired to the output pin. So up to the VGA driver, for the input memory value, we could just simply put the output of RAM here. Problem is that when the CPU is addressing video RAM. Of course, that's going to be in any order it chooses, which is not the address being asked for by video RAM. And so video RAM would wind up spooling for the particular address that it's asking for, it would wind up spooling garbage out to the screen, garbage being something that's being accessed by the CPU, which I guess is maybe as good as anything else, but I actually think it's better to just put all pixels turned off. So there needs to be some arbitration here to either pick the value coming out of RAM based upon whether or not it's coming from the VGA driver being the one doing the asking, or spooling out zeros because the last clock tick asked for video RAM. So that's actually the key here, because remember, VGA driver is going to spit an address out, and then the next clock tick, it's going to be getting the data value back because, of course, all this RAM is synchronous. So there's two things that we need then. We need a multiplexer to select whether or not the value that we want into the driver is coming from RAM or is simply zeros. And then we need a flip-flop to delay by one clock tick whether or not on the last tick we were accessing video RAM. So the normal case will be we want the output from RAM to be fed into the VGA driver. Otherwise, the CPU has control, so we're just going to send the VGA driver zeros. So for the selector of the mux, remember, it's whether or not we were accessing RAM from the last clock tick. So let's do that with a flip-flop. The input of the flip-flop being the output of this VRAM access control component. So let's put a flag or a tunnel. And wire that as the input to the flip-flop. And then, of course, now the output of the flip-flop is just going to be wired directly to this mux. So let's create a test. And what I'd like to do is create a test that actually does something on the screen motion-wise. Most of my other tests have been rather static, so let's create a component. We need a screen, obviously, and we need a clock, and obviously we need to output pins for VGA interface. Whenever we load the screen, we're just going to load it with all ones. Now, my idea is that after a bit of delay, then we want to address some video RAM and load it with ones, and then delay a little more, and then load the next address, essentially, basically filling up the whole screen, sort of a slow fill of white from top to bottom. So to do that, let's just put a counter in. I'm just going to estimate maybe a 16-bit counter to give us a delay. And we'll just make sure it counts up. And we'll just make it free run so that it always counts. So when this counter overflows, then we want it to increment essentially our RAM, our screen address input. So let's put another counter in to keep track of that address. And again, this needs to be a 13-bit counter because we have 8K of addressing to cover here. So again, we want this one to, again, always count up. And we want this one to count once our delay overflows. So the output of this counter then is what's going to get fed into the address of the screen. However, we have to do an address conversion. So to achieve that, we need to convert our 13-bit address to a 16-bit address starting at 16,384. So our video RAM starting at that byte is referenced by this bit being a 0, and that bit being a 1, and that bit being a 0. Now we don't want to present this address every single clock tick because that's not really a good simulation of what the CPU is going to do. So I would suggest that we only present this address when this ticks over. So in order to do that, let's hook up a flip-flop such that once this overflow occurs, then on the next clock tick, we'll take this address and present it to the address of the screen. So let's use a flip-flop to do that. In order to present a different address to the screen at times other than when this transition is occurring, let's use a multiplexer. And if we're not in this transition, then let's just present zeros to the screen. Which will simulate an address like the CPU might be accessing. Otherwise, we'll present the address from our address counter. Oops, that's this connection. And then selecting that, of course, will select a 1 when this flip-flop, or actually when this ticks over on the next clock tick. So when do we load this value? Well, we load this value at the point that this signal right here is high. So let's put a tunnel. We should be able to synthesize this now. Let's try it. Okay, synthesis is done. Let's load the design, see what happens. Pushing the program button now. And it looks like it completely worked. And of course, I got a little hum, so there must be some filtering that needs to be done with my audio. But in any case, I think the circuit's working. Thanks for watching.